So we'll start the live session now. I hope all of you can see my screen, right? Is my screen visible? Am I audible? Am I audible? Anybody? Reshlin Ritan Raj, CCAS, BOFGH, main something. Am I audible?
Yes, sir.
Okay, so we can continue with the session. So this is our problem statement for today. So you remember the three parameter and four parameter viscoelastic models, right? Just for a review, the model we will be using today is the four parameter Burgers model, which is depicted by this diagram. This end is fixed and this end is applied by sigma stress and epsilon strain. So this is E1 and eta 1, this is E2 and eta 2. So this is just for the sake of completeness. I'm giving you the expression, the actual expression for this Hooke's law. So this is sigma double dot plus E1 upon eta 1 plus E2 upon eta 2 sigma dot plus E1 upon eta 1, sorry, E2 upon eta 2 sigma, this is dot, is equal to epsilon double dot E1 plus E2 plus epsilon E1 upon eta 1 E2 upon eta 2 eta 1 plus eta 2. So just as an exercise, you can try it by yourself and you can let me know if I have done some mistake or it is correct. And if there are any questions regarding that, you can post it on discussion forum anytime. And right now in this question, what we use is we use E1 equal to 10, E2 equal to 20, eta 1 equal to 1, eta 2 equal to 1. So I have not taken any standard value or some experimental value. I'm just taking it for the sake of solving a problem, for demonstrating the solution of this problem. The actual values may differ significantly in an actual scenario. So we can write the governing equation as the governing equation can be rewritten as sigma double dot plus 30 sigma dot plus 200 sigma is equal to 30 epsilon double dot plus 400 epsilon dot. And now there is a force sensor which is placed at the base of this system. And what we do is we measure the force there and we assume that it is unit cross section area. So force is equal to stress. So F is equal to sigma can be used. And if we remember, the state space expression is actually the state space representation can be given as x dot vector is equal to A matrix multiplied by x vector plus B matrix multiplied by U vector. Then this is the sensed variable y vector is equal to matrix C into vector x plus matrix D. So this is the input variable, this is the exciting variable, and this is the sensed variable. So using this expression, what we actually need to find for state space representation according to the question is, we have to find the controller canonical form, observer canonical form, and Jordan canonical form. So first we'll go for the controller canonical form. So if you remember, if the equation is given as yn plus alpha 1 yn minus 1 up to alpha n minus 1 y dot plus alpha n y dot. So these are nth derivative with respect to time, n minus 1 derivative with respect to time, and this is just a representation. So it need not be actually time, it can be different variable in many cases, but we are right now taking it as time. And equal to beta naught into u nth derivative plus beta 1 u n minus 1 plus up to beta n minus 1 u dot plus beta n u. So right now y is equal to f, but f is equal to sigma, so y can be written as directly as sigma, and u is basically epsilon. So what the problem statement says, that there is a fouling problem. Fouling is basically, if this is a beam, there is another object, like there is another object which can move in this direction. So what happens is, due to this object's movement downwards, there is a constant displacement or constant strain that is introduced in the system. So this beam comes to this new position. So this position is actually constant. So actually epsilon is the input variable in this case. Usually the stress or the force is input variable, but in this case it is strain. And due to that strain, there is a stress induced in this system, in this axial direction, shear direction, as well as the other directions. So due to this stress induced in the system, there will be a chance of failure. So there is a maximum amount of stress which this component can handle, and that is why we are calculating the amount of stress which is induced by this fouling component. So what we want to do is, we want to measure or control the stress induced in the system due to the applied strain. So if we see the equation, we were given the equation as sigma double dot plus 20 sigma dot plus 200 sigma is equal to 30 epsilon double dot plus 400 epsilon dot. So if we compare these two equations, what will be the value of alpha 1? Alpha 1 will come as, okay, this is up to double derivative. So first of all, we'll define n. So n is equal to 2 here, because the maximum derivative observed here is 2. I'll just change the color. Hmm. N is equal to 2. So n minus 1 alpha 1. So next derivative alpha 1 is equal to 20. And the next one is alpha 2 equal to 200. We don't have any more variable in the series, so we'll stop here. For beta, we have this beta naught with maximum derivative. N was equal to 2. So here epsilon double dot has a coefficient of 30. So beta naught is equal to 30. Beta 1 is the next one less derivative, which is 400. So we can write it as 400. And beta 2, which is the next derivative, which is plus 0 epsilon. So beta 2 is, sorry, beta 2 is 0 here. So right now we have these variables. And if you remember the class lectures for controller canonical form, first part says, as here, the first part says this controller canonical form. So if we go for controller canonical form, A is basically 0, 1, 0, something 0, then 0, 0, 1, 0. And in the last row, we have minus alpha n minus 1, minus alpha n minus 2, up to alpha 1. With a minus sign. So substituting from the previous equation. So n is equal to 2. So we have 4 entries. 1, 2, 3, and 4. And for those entries, we can see from here, alpha 1 is 20, alpha 2 is 200. So n is equal to 2. So here will be alpha 2. So minus 20. And the second one is minus 200. This is the second entry. This will be 1. And this is the first entry, which is 0. So we get A matrix. Then for B vector. So B vector is, as per class lectures, it is in controller canonical form given as 0, 0 up to last value is 1. Until then, everything is 0. So in this case, because the value of n is equal to 2, so what we will have here is just 0 and 1. So we have value of B as well. Now for C, sorry, for C, there is this expression given. It is a row matrix beta n minus alpha n beta naught. Then sorry, I'll just write it closer. Minus alpha n beta naught, beta n minus 1 minus alpha n minus 1 alpha naught dot 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 beta 1 minus alpha 1 beta naught. So if we substitute these values, so what will be beta 2 minus alpha 2 beta naught? So here we see beta 2 is 0, alpha 2 is 200, and beta naught is 30. So it will become minus 6000, minus 6000. And beta 1 minus alpha 1 beta naught. Beta 1 is 400, alpha 1 is 20, and this is 30. So this will be Okay, wait. Have I done something wrong? Alpha 1 is 30. If I have, yeah, alpha 1 is 30. I had written it incorrectly here. Just make it a correction. So alpha 1 is 30, beta naught is 30, and beta 1 is 400. So what will happen here is it will become 400 minus 30 into 30, 900, which becomes minus of 500. So C will be equal to minus 6000 minus 500. And D matrix is simply beta naught value, which is, we know from here, beta naught is 30. So we can simply write it as 30. So we have found A, B, C, and D. This is the controller canonical form because the controller matrix is actually the of this form. Then we have this observer canonical form. So for observer canonical form, in the second part, if you remember, we had to do the observer canonical form. For observer canonical form, A is of the form minus alpha 1 minus alpha 2 dot 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 up to minus alpha n minus 1 minus alpha n. And the next is 1, 0 up to 0, 0, 1 up to 0. This is 0, 0, and this goes to 1 and 0. Because see, this value is 0 because this is the main diagonal. This is the super diagonal. This is the diagonal next to the main diagonal. The one, this row of this array of 1 is not on the main diagonal. It is on the offset by 1 upwards. So that you should remember. So right now, because the system has n equal to 2, we just have 4 values. We'll try to find them. So this is alpha 1, alpha 2, alpha n. So what is alpha 1 here? Alpha 1 is 30. So we can directly write it as minus 30. Alpha 2 is 200. We can write it directly as minus 200. Then for, okay, if we see here, this value will be 1 and the bottom one will be 0. So this is the A matrix. Sorry. For B vector, what we will do is, here because it is an observer canonical form, this forcing matrix is not maintained as unity, but the C vector is actually made as one entry as unit and all other as 0. So the observer matrix is controlled. So B vector can be written as B1 beta 1 minus alpha 1 beta naught, beta 2 minus alpha 2 beta naught up to beta n minus alpha n beta naught. So because n is equal to 2, we have only 2 entries. So beta 1 minus alpha 1 beta naught is, we know beta 1 is 400, alpha 1 is 30, beta naught 30. So it will become 400 minus 30 into 30, 900, which is same as previously calculated here. as minus 500. So we can actually directly write it as minus 500. Then for the second value, beta 2 minus alpha 2 beta naught, that is also calculated here, which is minus 6000. So we have found B as well. So because it is a observer canonical form, the C matrix is nothing but 1, 0 up to end. Because it has only two values, C is actually 1, C is actually 1 and 0. And D is simply equal to beta naught, which is equal to 30. So we have found the observer canonical form as well. A is found, B is found, C is found, and D is found. So these are the two commonly used forms. But there is one other form which is called Jordan canonical form. So it has some special benefits. Actually, the further calculation becomes much easier. We'll deal with that when we will work on this observability and controllability, which are two basic parameters which indicate that if the system can be effectively controlled or observed. So the third part, as it says, is the Jordan canonical form. So the initial part is a bit lengthy. So if you remember the class lectures, it is written as y is equal to, actually, if this is the differential equation yn plus alpha naught yn minus 1 dot 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 alpha ny is equal to beta naught un plus beta 1 u of n minus 1 up to beta n u. So if we take the Laplace transform and we y bar s, we express it as y bar s equal to beta naught plus p1 by s minus lambda 1 plus p2 by s minus lambda 2 up to pn by s minus lambda n u of s. So this is the form we express it as, the transfer function. And we should remember that because this is expressed in this form is only possible if all the eigenvalues are independent. All the eigenvalues are unique. If the two eigenvalues come as identical values, then this Jordan canonical form cannot be expressed directly. So for this, what we do is we have this direct solution as a equal to lambda 1, lambda 2 up to lambda n. All other values become 0. So it is basically a diagonal matrix of this lambda 1, lambda 2 up to lambda n. B is expressed as each entry is identity 1. C is expressed as this P1, P2 up to Pn, and D is as usual beta naught. Sorry. So we will derive this form for this particular uh, system. So we have the system sigma double dot plus 30 sigma dot plus 200 sigma is equal to 30 epsilon double dot plus 400 epsilon dot plus 0 epsilon. So what we'll do is we'll take the Laplace transform. So s square sigma plus 30s sigma plus 200 sigma. We'll keep the bar to show the Laplace transformed variable. 30 s square epsilon bar plus 400 s epsilon bar plus 0 epsilon bar. So on the left hand side we can write s square plus 30s plus 200 sigma bar is equal to 30s square plus 400s epsilon bar. So sigma bar can be expressed as 30s square plus 400s upon s square plus 30s plus 200 into epsilon bar. So this transfer function is currently not in the form of this particular required form. So we'll convert this transfer function into this particular form. So for that, the first step is we separate the beta naught. So for separation of beta naught, we can simply write it as 30 into s square plus 30s plus 200 minus 30 into 30s plus 200 plus 400s whole divided by s square plus 30s plus 400, and outside we have epsilon bar. So we discussed initially that this is similar to u and this is similar to y because sigma is equal to f. So we can directly use it. So this gets cancelled out. We can take it separate, and this remains with this denominator. So we can directly write it as sigma bar is equal to 30 plus 400s minus 30 30s plus 200 upon s square plus 30s plus 400, and this is epsilon bar. So this can be written as 30 plus 400s minus 900s minus 6000 upon s square plus 30s plus 400 epsilon bar. This is 30 plus, in numerator we have minus 500s minus 6000, and in denominator we have s square plus 30s plus 400 epsilon bar. So we can factorize the denominator, right? So the denominator is simply a quadratic equation. Sorry, I'll just come back to this one. So for s square plus 30s plus 400, we can simply write it as s is equal to minus 30. We are finding the roots here. So minus 30 plus minus square root of 30 square minus 4 into 400 upon 2. Sorry, upon 2. So it will become minus 30 plus minus square root of 900 minus 800 by 2, which becomes minus 30 plus minus square root of 100 by 2. So s becomes minus 30 plus minus 10 by 2. So here we can write, we'll write on the next page, s is equal to minus 40 by 2 and minus 20 by 2. So this s square plus 30s plus 400 can be expressed as S plus 10, S plus 20. We could have done it directly, but just for direct approach, we use this formula directly. So this we know now. So we can write this equation now as sigma bar is equal to 30 plus minus 500 S, sorry, minus 6000 upon S plus 10 and S plus 20. So if we expect this form to land as this form, so it will be something like P1 upon S plus 10 plus P2 upon S plus 20. It will be equal to minus 500 S minus 6000 upon S plus 10 into S plus 20. So we'll take the common factors here. So we can write S plus 20 into P1 plus S plus, sorry, S plus 10 into P2 upon S plus 10 S plus 20. This can be written as P1S plus 20 P1 plus P2S plus 10 P2 upon S plus 10 S plus 20. So we can further write it as P1 plus P2 S plus 20 P1 plus 10 P2 upon S plus 10 S plus 20 is equal to this. We know the expression minus 500 S minus 6000 upon S plus 10 S plus 20. So by comparing the coefficient on both sides, S coefficient will give P1 plus P2 is equal to minus 500, and constant coefficient or coefficient of 1, it will give us 20 P1 plus 10 P2 is equal to minus of 6000. So we can do a much simpler approach. 10 P1 plus 10 into P1 plus P2 is equal to minus 6000. We know P1 plus P2 is equal to minus 500, so we can write 10 P1 plus 10 into minus 500 is equal to minus 6000. Thus 10 P1 minus 5000 is equal to minus 6000. So 10 P1 is equal to 5000 minus 6000. 10 P1 is equal to minus 1000. So P1 can be written as minus of 100. This implies that minus 100 plus P2 is equal to minus 500. So this gives P2 equal to minus 400. So now we can directly write, we know P1 and P2. So sigma bar, which was given as 30 plus minus 500 S minus 6000 upon S plus 10 S plus 20. This can be written as 30 plus minus of 100, because P1 was the numerator for S plus 10. So minus 100 by S plus 10 and minus 400 upon S plus 20. So now we have this in the required form. So we can directly apply the Jordan canonical form. So here lambda 1 is minus 10, lambda 2 is minus 20, n is equal to 2, we already know that. Beta naught is equal to 30, P1 is equal to minus 100, P2 is equal to minus 400. So these are the required variable for Jordan canonical form. So using this, we can write A as, what was lambda 1? Minus 10, minus 10, 0, 0, minus 20. Lambda 1, lambda 2. B can be directly written as 1, 1 because n equal to 2. C can be written as series of P1, P2. So P1 is minus 100, P2 is minus 400. So we can write it as minus 100 minus 400. And D we know is equal to beta naught, which is 30. So we can directly obtain, sorry, we directly know the Jordan canonical form. So if we remember, there was this discussion during class lectures that we need to figure out if the system is controllable. We need to check the controllability of the structure of the system. For that, we make a C matrix, and which is equal to a matrix of this B, sorry, B vector, then AB vector, because it is a 2 by 2, 2 by 2, n equal to 2. We don't need to go any further, but it is usually a n minus 1 B. So we have n equal to 2, so we only need to go up to B and AB. So right now we know B. B is 1, 1. So for C, we can write the first column as 1, 1. For second column, we need to calculate AB. So we know A is minus 10, 0, 0, minus 20. Now, one thing to notice here is if we would have used this, sorry, this observer canonical form or the controller canonical form, the A matrix is relatively much complex or having much more values. B is relatively simple. In observer canonical form, C is relatively simple, but usually A is a little bit difficult to handle. So using Jordan form, the Jordan canonical form, these calculations become much easier. The initial calculation is a bit lengthy, but later on we can formulate much easier. So if we calculate AB, A was minus 10, 0, 0, minus 20, minus 10, 0, 0, minus 20, and B is 1, 1. This comes out as, first we multiply this becomes minus 10, then this with second one, this becomes minus 20. So this becomes minus 10, sorry, this becomes minus 10, this becomes minus 20. So the rank of this matrix, because none of these rows or columns are identical, so rank of this matrix remains as 2. So rank is 2, which means The order of the system is same as the rank of this controllability matrix. So this system is controllable. Conclusion is system is controllable. Now, if this usually one more thing we check is if the system is observable. So for observability in the system, if we can observe the system completely or sense the system completely, so for that we use O matrix with a cut on it, and we write it as C A transpose C A square transpose C up to A n minus 1 transpose C. Because n is equal to 2, we only need to go up to C A transpose C. So C we have calculated here, it is minus 100 minus 400. So right now we are using C of the form minus 100 minus 400. We are writing in this form. We can write it in other form as well. In that particular form, it becomes as C and CA, something like that. But this is just a totally flipped kind of representation. So both of them are actually correct. But as we are following the class lectures, we will not be using this, and we'll only stick to this, so nobody gets confused. So we can use this observability matrix as C. We know that minus 100 and minus 400. For the other two, we use A transpose C. So what was A? Minus 10, 0, 0, minus 20. So diagonal values are only diagonal values are there. The other two terms are 0. So it doesn't matter if we take transpose or not, the matrix will remain same. So we can write it as A transpose C is equal to minus 10, 0, 0, minus 20. So transpose is same. So we are not writing transpose again. So C is, as we have calculated, minus 100 and minus 400. So minus 100 minus 400, which comes out as minus 1000 and minus, I think, 8000, right? Go to 8, yeah, right. And this minus gets cancelled because both are negative. So this can be written as, sorry, 1000 and 8000. So in this case as well, there are no two rows or columns which are linearly dependent. They are linearly independent, and that is why the rank here is 2, which is equal to n of the system. So this system is completely observable as well. So we have checked for observability and controllability. So any questions till now? Any questions?
No, sir.
We can move forward, right? We can go ahead. If anybody has doubts again, so I'll be uploading this video on YouTube as well, which is accessible through that NPTEL portal, and you can review it again. And if you still have doubts, you can post a question on discussion forum. So we have covered the controllability canonical form, controller canonical form, observer canonical form, Jordan canonical form. And I have used the Jordan canonical form to check for controllability and observability. But you can see that the same result or the same result for controllability and observability will be obtained using the other two forms. The metrics may differ, it is possible, but the the results, which is the if the system is controllable or not or observable or not, they will not change. So the other thing during the lecture was we used expression for exponent of a matrix. We used this term, we were multiplying e raised to power at, where a was a matrix. So because we have not covered it till now in the coursework, so I just wanted to review this exponent of a matrix for those of you who don't know it. So usually uh, what we do is we know the expansion for e raised to power x, right? The Taylor expansion 1 plus x by 1 factorial plus x square by 2 factorial plus until infinity x raised to power n by n factorial and so on. So same goes for this matrix. E raised to power a matrix is basically 1, or here it becomes identity matrix plus a matrix upon 1 factorial plus a matrix square by 2 factorial plus a matrix cube by 3 factorial up to infinite. So, but this is quite tedious to calculate. So for some special cases, this becomes much easier. Like for symmetric cases, there is an orthogonal decomposition possible such that a matrix can be expressed as x inverse lambda x. So this x is the eigenvector and lambda is the eigenvalue. So what we do here is this x is x1 vector, x2 vector up to xn vector, and lambda is basically lambda 1, lambda 2 up to lambda n 0, sorry, 0, 0. So this is expressed in this way. So if we use this form, we can calculate a square such that a is multiplied by a. So a can be expressed as x inverse lambda x. So x inverse lambda, sorry, x, then x inverse lambda x. Now these two, this is x and x inverse multiplied. So this will result in identity matrix. So x inverse lambda I lambda x. So what will happen here is x inverse lambda lambda x, and this will finally result in x inverse lambda square x. So similarly, you can do for any a raised to power n. If we express it in that form, it can be written as x inverse lambda raised to power n x. Now this is again a power of n, but actually due to it as a diagonal matrix, it becomes much easier to solve. Like if it is a b 0 0 multiplied by a 0 0 b. So if we multiply this, this becomes a square plus 0, 0 plus 0, 0 plus 0, 0 plus b square. So this becomes finally a square 0 0 b square. So for any diagonal matrix, the square is basically the square of its elements. So this lambda raised to power n can be simply expressed as lambda 1 raised to power n, lambda 2 raised to power n, up to lambda n raised to power n. So using this thing, we can actually calculate this, sorry, we can express it as capital A raised to power n is nothing but x inverse lambda I raised to power n into x. So if we use this and we substitute it in e raised to power a matrix. So this is identity plus a by 1 factorial plus a square by 2 factorial plus up to series expansion. So we write it as I plus, sorry, I am dropping the matrix sign, but it is there. X inverse lambda x 1 factorial plus x inverse lambda square x by 2 factorial plus x inverse lambda cube x by 3 factorial and series. So this can be rewritten as x inverse x plus x inverse lambda by 1 factorial x plus x inverse lambda square by 2 factorial x, x inverse lambda cube by 3 factorial x, and so on. So we can take x inverse on this side common, and we can give I plus lambda by 1 factorial, sorry, lambda square by 2 factorial, lambda cube by 3 factorial up to series, and on the other side we can have x. So we just need to solve this central value. So e raised to power a matrix is x inverse. Now if we see, it is basically a matrix of 1 1 1 1 up to this thing. Then this is 1 by 1 factorial lambda 1 lambda 2 up to lambda n. Then this is 1 by 2 factorial of lambda 1 square lambda 2 square up to lambda n square. Then we have lambda 1 cube lambda 2 cube lambda n cube 1 by 3 factorial, and we have closing as x. So if we take this inside and sum these matrices, it will be equal to x inverse 1 plus lambda 1 by 1 factorial plus lambda 1 square by 2 factorial. The second term will be 1 plus lambda 2 by 1 factorial plus lambda 2 square by 2 factorial, and so on up to 1 plus lambda n by 1 factorial plus lambda n square by 2 factorial, and that series, and the other side is x. So if we see, this is the expansion of e raised to power lambda 1, e raised to power lambda 2, e raised to power lambda n. So this can be actually, sorry, okay, we have maxed out on number of slides. I'll just use a new whiteboard. So we can directly write this e raised to power a as x inverse. This is e raised to power lambda 1, e raised to power lambda 2, up to e raised to power lambda n into x. So x inverse e raised to power lambda I matrix and this. So e raised to power a matrix. So if we know the eigenvalues and eigenvectors of A, and A is a symmetric matrix which can be expressed as x inverse A, x inverse lambda x, sorry, x inverse lambda x. So we can directly find the this exponent of the matrix, and we can use it directly to find the solution of that matrix. So any questions regarding this? Anybody? Any questions regarding this or anything regarding the course which is not clear to you? Because this is the last live session. So there won't be any more live session for this particular course. So if you have any questions, you can ask them right now. Okay, so in that case, we'll just review what we have seen till now. So in this live session, we first saw this 4 parameter viscoelastic model by Berger. So this one is one of the two types of Berger model discussed in the class. So this is actually the expression we get using these values. We get this particular equation, and using this equation, we try to find the state space representation of the system. And for that, first we use the, if this is the form of differential equation, the governing differential equation, then we can find the value of n alpha 1, alpha 2, beta naught, beta 1, beta 2 according to comparing these two equations. This is the equation which is found using this relation, and this is the generalized equation for the state space formulation. So using the controller canonical form, this is the expression discussed during class. And using this expression, because we have n equal to 2, we have a 2 by 2 A matrix in which these values are obtained. Then we have this B matrix, which is a standard matrix. Its value does not change. Then we have this C matrix depending on the value of alpha I and beta I. So using these values, this is the C matrix we obtain. And then there is this D matrix, which is basically the value of beta naught. It is a 1 by 1 matrix or a scalar value, whichever you want to consider it as. And then we have this observer controlled, observer canonical form. This is also discussed in class. So the direct formula is given. So in this case, the alpha I values are along the first column rather than the last row, which was in the controller canonical form. So they are in first column, which are placed like minus 30 and minus 200. And the rest is, because it is a 2 by 2 matrix, this is the final form obtained. Because it is an observer canonical form, C matrix is having the fixed values and B matrix is to be calculated using alpha I and beta I. This is the formula given, and using this, this is the values we obtain for B. And D is again equal to beta naught, which is equal to 30. So then the third case is the Jordan canonical form. For that, what we this is. Jordan canonical, sorry, form. So in Jordan canonical form, we need to express this as a transfer function, and that transfer function need to be in this form. So if it is expressed in this form, and one of the requirement is the lambda I, the lambda 1, lambda 2, lambda 3, all should be unique. All eigenvalues should be unique. So we can express it as beta naught plus p1 by s1 minus lambda 1, p2 by s minus lambda 2, and so on. And then we can have A equal to the diagonal matrix having these eigenvalues, and then B equal to unity, all entries are unity, C equal to the P1, P2, P3 up to Pn, and D equal to beta naught. So we find the Laplace transform, we take the transfer function, and we use mathematical manipulations to finally obtain the form, the desired form, which is this. So we get this form, and using this form, we obtain the lambda 1, lambda 2, beta naught, p1, p2 for n equal to 2, and we use it to finally find the Jordan canonical form of the state space formulation. And for the further calculation, we use this form of C and not this form. So for the ease of calculation, ease of representation actually, calculation will remain the same, but ease of representation, we use this form, not this form. So for that, we use the controllability matrix, which is for 2 by 2 matrix expressed as B vector and AB vector. And using this, we find this rank is equal to 2, which is same as the order of the system, and that makes the system is controllable. So for the observability of the matrix or the observability of the system, we use the C matrix, a C vector actually. So C and A transpose C is used because this is A transpose C because we have considered the C in column vector form and not a row vector form. So when we find this observability matrix, the rank is again equal to 2, which is same as order of the system, and therefore the system is observable as well. And then we go on to actually find the exponent of a matrix, which was utilized in one of the problems in the class. And finally, if we can express this A matrix as x inverse lambda x, this is the key thing actually. Otherwise, you have to use this form actually. This whole expansion needs to be solved if the A matrix cannot be expressed in this form. But if it can be expressed in this form, we can directly go on to expressing it as in this particular form. So this is for now. And if you have any questions, feel free to ask right now. I'll wait for 5 minutes if anybody wants to ask. And after that, we'll be ending this session, and you can ask the question or discussion forum, or otherwise, we'll see you during the exam, the final exam. Thank you. Okay, the guys have left, so I'll be ending this session right now. Thank you.